Okay. Oh, this you're watching the actual processing of this thing. It says, oh, it went to public. It'll say private world. Uh, Whatever. All right. Well, let's get back to our discussion here, shall we? All right. So now let's take a look. All right. So let's take a look at this proton. All right. Well, let's put a proton here. Let's put a positive charge here. All right. For that proton to move from here to here along this potential field line, for it to go, energy required, change in electric potential energy required to do that is equal to zero. Okay? All right, so let's just do it down here. Positive charge, and let's say this is even a negative 200 volt field line. Okay, or not field line, potential difference line. To move from there to here is the energy required. The change in electric potential energy is equal to the change in electric potential energy is equal to um, the charge Q, say this is some charge Q, times the change in voltage. Well, what's the change in voltage? There's your equation for the electric potential energy. Change in voltage. All right, well, if the voltage is given. So you got this. You go, well, all right, that would be Q times negative 200 minus negative 200, because that's where it went from. That equals zero. No energy required. Let's move it. Let's try it one more time. Let's do this, though. Same positive charge. Let's say it's 3.0 microcoulombs. Okay, positive 3. And it's on a negative 200 volts. All right, and it's going to move from here, and I want to drag it, and it doesn't depend on the path I take. It does not depend on the path because all the forces are conserved here. Energy is conserved. All right, and let's say I want to move it over here to the positive 100 volts. Okay, now since this is positive 100 volts, I know that there's a bunch of positive charge over here that's creating that positive 100 volts. So I move it over to here, and the electric field lines, which are parallel here, are coming out this way. Okay, here's my electric field lines going through here. All right, and they're all perpendicular to the, and they just keep going. I mean, they're constant too. And so I want to see what my change in it. Now, this positive charge does not want to go here. So an outside force has to take it from here to here. If we just do the algebra, we'll see that it's going to gain potential energy. It's going to gain electric potential energy because I know that the change in electric potential energy is equal to 3.0 microcoulombs times final V2, this equals V2, and this is equal to V1. So we do V2 minus V1, which would be 3.0 microcoulombs times 100 minus negative 200, which gives me positive 300. So I've got 3.0 times 10 to the negative 6 times 3.0 times 10 squared, which is 300. And that gives me 9 times 10 to the 4th joules. It's how much energy that thing gained. If I let it go, it's going to go slamming back there and gain kinetic energy. All right? Now, let's look at a parallel plate where we've got straight field lines and we've got straight voltage lines. That'll be the next thing we do. And you're going to see another thing on the electric field, the relationship between the electric field and the voltage, besides that they're perpendicular to each other. Okay, so let's look at that one.